Welcome, everybody. We're going to be going through part one of MCAT metabolism today. So on our agenda, we're going to start by talking about digestive enzymes and transport of food molecules. Then we'll be hitting glycolysis, pyruvate dehydrogenase complex, and citric acid cycle. There is gluconeogenesis in the handout. If you're one of the people attending, you're getting the handout. There is gluconeogenesis in the handout, but because of reasons, we're not going to cover it in this recording. That'll be covered in the next recording, along with hopefully we can get to fermentation and Cori cycle, glycogenesis, and pentose phosphate pathway, and maybe electron transport chain for next session. Right. So intro to metabolism. So metabolism is one of the most difficult MCAT topics for students to master. Alexa,
set a 10-minute timer.
Whoever's mic is on. A thorough understanding of metabolism will reinforce OCHEM reactions, redox, reduction oxidation, enzyme classes, bioenergetics, macromolecules, cell structure, digestion, and more. So metabolism is kind of one of those higher level topics that connects so many different medium, lower level topics together that are, we're learning OCHEM reactions. We're usually learning them discretely. But we're going to see a lot of OCHEM reactions that we've encountered previously when we go through metabolism. Tips for metabolism. If you can connect enzyme names with substrate names, as well as bond changes, that is going to reinforce all of your understanding. It's going to make things stick much longer, and it's going to make you understand what's going on much better. So that's going to be one of the focuses of going through metabolism together. Looking for patterns. So you want to be looking for any patterns that you can, like, okay, this happened in step 3 of glycolysis, and something similar happened in step 7 of citric acid cycle, or something like that. And that'll also help this stick better and longer. Ask, why is this happening? Why is this thing being oxidized? Why is this thing being reduced? Where did this oxygen come from in the molecule? And a narrative understanding is superior for metabolism to brute force memorization. So one of the common mistakes people will make when they're trying to learn metabolism is they'll just memorize all of the reactions discretely, as opposed to like a narrative understanding from A all the way to Z. And again, this is another tip that'll help things stick for better and longer. Just a general tip, I recommend getting a whiteboard. You don't have to get a huge one like the one that I have necessarily, but like it could just be like a little like desktop whiteboard. It's just so much easier than like pencil and paper, erasing, using multiple pieces of paper. And one thing that I did when I was learning metabolism for the first time, and probably the second and third time as well, throughout the years, was on a whiteboard. So write down the entire pathway you're trying to learn. Say it's glycolysis. Erase all the intermediates and then fill them back in, or maybe just erase the first 5 intermediates and then fill them back in. And erase all the enzyme names and see if you can fill the enzyme names back in. And then rinse and repeat. This will serve you well for MCAT and med school. A lot of my med student friends do have some kind of like whiteboard that they use for like learning complex pathways and stuff like that. Any questions before we keep going? All right, so we're going to start in the mouth, and so food is going to enter. They call it the alimentary canal. This is your mouth all the way to your gut, all the way to your butt. So the food will enter the alimentary canal, and you're going to grind it up with your teeth, break it into smaller pieces. Because anything you don't break down with your teeth, your stomach is going to have to break down, and it's not as good at breaking things down as your teeth are. And then we'll move down the esophagus. So this is our esophagus. There's going to be a sphincter here. Anybody remember the name of the sphincter at the bottom of the esophagus, top of the stomach?
Isn't it pyloric?
Oh, so the pyloric is at the bottom of the stomach, top of the small intestine. So it has a counterintuitive name. It's actually called the cardiac sphincter. Now, why would it thing that connects your esophagus and your stomach be called cardiac sphincter? Cardiac means heart, right? And it's because it's close to the heart. Yeah, it's close to the heart. That's why. They could have come up with a better name. Esophageal sphincter. That has a nice ring to it. I mean, is there esophageal sphincter?
Isn't there one? Yeah.
I feel like there should be, but yeah, anyways, we'll keep going. Peristalsis, we know peristalsis is when a tube is like you're basically squeezing through using muscular contractions, almost like how we go down, like our action potential goes down a neuron axon, but instead it's like, it's actually contraction, like you're almost like trying to squeeze toothpaste through a tube is the way I've heard it compared to, and that's going to occur in the intestines as well. Then we'll end up in the stomach. We know the stomach is acidic. There are cells secreting HCl there, hydrochloric acid. And so that's where our, camera switching, that's where digestion is going to really kick in. Particularly, we're going to start hydrolyzing, proteins, and we'll have the help of a enzyme that we'll get to in a sec. Liver and gallbladder. So bile, where is bile synthesized?
In the liver.
Bile synthesized in the liver. We always almost want to say gallbladder, but we know that it's actually synthesized in the liver and then it goes to the gallbladder, right? And then we have we're starting to get into the stomach. Now we're getting into the small intestine. So bile will be deposited in the small intestine. And what is the bile for? Breaking down what?
Fat emulsification.
Perfect. Yes, emulsification. Excellent. Pancreas is going to have pancreatic enzymes that it's going to release, as well as hormones. Small intestines is where we're going to be doing the bulk of our absorption. So the small intestines have a lot of surface area. We're going to look at some villi in a second. And there's a lot of surface area for digestion. There's also we call brush border enzymes, enzymes that are on sort of the cell membrane of these villi. And they're going to have lots of surface area, lots of enzymes for lots of breakdown. Anybody remember what do we absorb in the large intestines?
I think the ADEC vitamins, I think. Then there's additional water.
Excellent. Yeah.
And I think even fat, if I remember.
I'd say probably more so in the small intestine for fat, but definitely everything else. Yeah.
Okay.
Yeah. Cool. And then anus. Here's a really cool diagram I found online that has a lot of organized information about where and when and what is getting broken down in which sort of compartment of the digestive system. So digestion is actually going to start in the mouth with salivary amylase. There's also lingual lipase that they kind of left out here. Salivary amylase and lingual lipase. What would lingual lipase be for breaking down? Fats, right? Lipase, fats, perfect. And then once we're in the stomach, the main thing that's getting broken down in the stomach is going to be our proteins under the action of pepsin. So that's that enzyme we were talking about a second ago. So proteins will be broken down into smaller polypeptides. We sometimes hear them referred to as oligopeptides. Once we're in the lumen of the small intestine, we're going to have amylase, which is from the pancreas, which is going to break down our polysaccharides even further into disaccharides and some monosaccharides. And then the brush border, we're going to finish sugar carbohydrate breakdown, breaking these guys all the way down into monosaccharides. And monosaccharides is what we know enters into like glycolysis, for instance. Maltose, what is maltose made out of?
Sucrose.
So sucrose is a disaccharide made up of glucose and fructose.
Maltose just has 2 glucose.
2 glucose. Or is it alpha beta linkage?
Alpha.
Alpha linkage, excellent. And then, so we'll continue with proteins now too. So polypeptides going to be broken down by trypsin, chymotrypsin into smaller polypeptides. And then more enzymes in the lumen of the small intestine, aminopeptidase, carboxypeptidase, are going to break these down into amino acids. And if we have any other small peptides left, brush border dipeptidases are going to break them into amino acids. So some of these are good enzymes to know, like aminopeptidase, carboxypeptidase, trypsin, chymotrypsin. You got to know pepsin, trypsin, and chymotrypsin for sure for the MCAT. You don't really talk a whole lot about like nucleic acid digestion. It is kind of weird to consider that, like, for instance, when you're eating a strawberry or something like that, which is made out of cells, they actually have like DNA in it. Or if we're eating, like meat would have DNA in it. A lot of plants that we would eat, but something like a potato or a yams, they're actually starch. So it's mostly in the middle, just starch. Now the outside is the skin, so that would have like DNA because there's cells on the outside. But like the inside of a potato is really just pure carbohydrate. And then fat digestion. So most of this occurring in the small intestine. We did talk about lingual lipase. That's kind of a minor player here because lipase doesn't really have a good way of breaking down fat globules. It's more for hydrolyzing triglycerides. So the bulk of the work is done in the small intestine for fats. We use bile salts, which we discussed, into emulsified fat droplets. And then lipase can then break those guys down into glycerol fatty acids. Any questions on this slide before we move on? Nope. Alrighty. Oh, I was supposed to put animations on this. Just gonna go ahead and hate to do it live, but it's gonna work better this way. Okay, so within the small intestine, so we have these little finger-like projections called villi. And the villi in the small intestine increase surface area available for enzymatic breakdown and absorption. The villi is also known as like sort of the brush border because it kind of like looks like the fingers of a brush, like a hairbrush as well. And they're going to contain all these enzymes. So we can see brush border enzymes, sucrase, maltase, aminopeptidase. So all those guys kind of chilling out here. We have transporters. So we have some glut transporters for glucose. I don't remember if this is another sugar. Yeah, this is another sugar transporter as well. And then the gluts are located here, it looks like, and here. So this is for getting it into the bloodstream now. And then we have tight junctions, of course, between our intestinal epithelial cells. Would tight junctions normally be leaky to water? Or do they not allow anything to pass?
Figure that they are not closed junctions, they are tight. Doesn't mean something should be able to still go through, I guess.
Yeah, yeah. So they can be leaky to water. Yeah, so they would have to have channels that can hold water, but they usually want to keep most other things out, right? So you can see nothing really else is going through here. We also have aquaporins, and then it looks like this guy's an amino acid transporter. So it's not that you need to know the names of these specific transporters, just kind of know of their existence. I don't know if you need to even know the names of the brush border enzymes, but kind of know that they're breaking down sugars and small peptides like dipeptides down to amino acids. So what type of transport is glucose subject to in this figure? The passive diffusion, facilitated diffusion, secondary active transport, or primary active transport.
Sorry, could you check that again? Sorry.
Would that be passive diffusion, facilitated diffusion, secondary active transport, or primary active transport for the glucose being transported right here?
Oh. This will be facilitated, I think.
Does facilitated diffusion have sodium go along with it usually, or is it usually just go straight through the channel? Nobody needs to come with it.
I think glucose is too big to just go through it. Something has to help take it in.
So it's not necessarily about glucose's size. It's more the fact that we're trying to absorb things. We want to get as much glucose out of the intestine as possible because we need glucose for a whole lot of things in our body, right? So therefore, glucose actually has to go up its concentration gradient from the intestine into these epithelial cells. So what is that sounding like? Up its concentration gradient, it has to be, is that passive or active? Yeah,
That's active.
Secondary
That's
active
active.
transport, somebody said in the chat. Perfect. Yes, active. Yeah. And we can tell it's secondary active transport because we have a sodium going along with it. Is that symport or antiport?
The symport.
It's symport. It's going in the same direction.
Yeah.
What type of transport are fatty acids subject to in this figure? They just look like they have a transporter, or they just kind of going through the membrane?
They go through the membrane straight up.
Yeah. So passive diffusion here. They also mentioned lipophilic xenobiotics. So xeno means alien, like xenophobia. So you could also say something is like, instead of xeno, you could say exogenous. So xenobiotics would be like drugs, so lipophilic drugs. And then, yeah, this was long thought to be the mechanism of fatty acid and steroid transport. It was long thought to be passive diffusion. And with steroids, in a lot of cases, it's true that they call it like the classical model of steroid uptake is they enter cells by just passing through the plasma membrane because they're so hydrophobic that they can just simply go through the plasma membrane. But it should make sense that it's a little more complex than that for at least fatty acids, right? Because fatty acids, we know, what would their charge be at physiological pH? Positive, negative, neutral?
It's negative.
Yeah, they'd be negatively charged. So it'd be hard to get through a membrane that has mostly hydrophobic if you're charged. So it turns out fatty acids will actually have transporters. So they'll have protein-mediated transport. And some steroids also have transporters as well, but for the purpose of the MCAT, assume steroids will diffuse through plasma membranes. Any questions on this slide here? All right.
So even for fatty acids, assume that it's passive diffusion for the MCAT?
You know, that's a great question. And I haven't necessarily encountered, like they ask us about steroids all the time. I haven't necessarily encountered fatty acids like where we had to assume that a fatty acid was crossing the membrane, probably because the MCAT's aware of a lot of these controversies and discrepancies. The writers are not dumb, they're scientists, they're MDs, PhDs, and MD PhDs. So they're aware of things like, remember how we were all taught in school that the reason why GC-rich DNA has a higher melting temperature is because of the triple bond between G and C?
Yeah.
That it's not necessary, it's not actually the case. It actually has to do with pi stacking interactions, where GC-rich DNA has better pi stacking interactions, and so the two strands are locked more tightly. So there is a question in the AMC somewhere where they ask about why does GC-rich DNA have a higher melting temperature? And one of the answer choices is better pi stacking interactions.
No, it's not.
Yeah. But the nice thing is they didn't put an answer choice that said because of the triple bond, because they're aware that people are still being taught these things in schools. So that's probably why we have just the reason for the anecdote. That's probably, and also you want to remember that when you do your AMC, because you'll get the question right then. The reason for that anecdote is there's probably a similar reasoning why I haven't seen them ask about do fatty acids diffuse through plasma membranes, because logically they shouldn't, but it was long thought that they did. Does that make sense?
It does, yeah.
Nice. All right, so let's go ahead and go more into fat digestion. So step number one, we have these large fat droplets in the small intestinal lumen. And the first step is that bile will emulsify these fat droplets. So it'll break them down, and then you'll have the bile is sort of represented by these little spikes on the outside. And then, so we'll then have the fatty acids and monoglycerides. So what would be a monoglyceride? A glycerol with how many with how many fatty acids? Just one, right? So a monoglyceride, a glycerol with one fatty acid. So these fatty acids and monoglycerides are then going to enter the epithelial cell. This figure is also assuming or leaving it ambiguous whether they'd go through diffusion or protein-mediated transport. But as we just discussed, it's probably not the case that they're just diffusing. Maybe the monosaccharide, because the monoglyceride would only have would not have a charge. So maybe that guy could, but I don't know, because glycerol also has those polar hydroxyl groups, so maybe not. Step 2 is going to be enzymatic digestion by pancreatic lipase. So, so this is occurring right here. So we're going to, if we have triglycerides that we ate in our food, breaks it down to here's our monoglyceride from here, and here's our 2 fatty acids. They say some free glycerol is also formed. And then once they're in the cell, the fatty acids are going to form triglycerides. And then in the Golgi, they're going to be packed by combining with proteins into chylomicrons. And they say absorption of products of fat digestion depends on size. So short and medium chain fatty acids and glycerol, which are all small relative to like a triglyceride or a fat droplet, would be absorbed into the blood via capillary. So short and medium chain fatty acids, as well as glycerol, can just go through the bloodstream. And that's because they will have, the fatty acids will have a charge. And if they're short and medium chain, they don't have as much of a hydrophobic tail. The longer the hydrophobic tail, the more likely it's going to be insoluble in water. However, long chain fatty acids, monoglycerides, are going to form into triglycerides. So they're going to go back into triglycerides like here, and then get transported in chylomicrons via the lymph system, the lymphatic system. Here we see what they're talking about: chylomicrons extruded from the epithelial cell and entering a lacteal, which is a duct or a vessel in the lymphatic system. Why do we have to use this lymphatic system? Like, why can't we just have these proteins going through these fats going through the blood? Why do we need to transport them in the lymphatic system? What could be the problem if they're in the bloodstream? These chylomicrons.
We'll clog it, I guess.
They could clog it up. Where would they be most likely to get clogged and slow the thing down? Which blood vessel? It would be aorta, arteries, arterioles, capillaries, venules, veins. Yeah, atherosclerosis, person said in the chat. Yes, exactly, Fernanda. Maybe not coronary artery, maybe coronary artery. I would say most likely they're gonna start by getting stuck in the capillaries. We really don't want that to happen, because that's gonna block up our bloodstream. Yeah, and then they could also, yeah, atherosclerosis. So it's not so much that it's the size of the blood vessel, it's just that they kind of stick to, I'm pointing at my heart, they kind of stick to the side, and then over time they build up a plaque.
Yeah, the walls, yeah.
Okay. Cool. All right. There's a composition of different fat particles. We have chylomicrons. So this is the first thing that enters the lymphatic system. So the lymphatic system is better than the bloodstream because the vessels are much larger. So you're less likely to get some stuck. Chylomicrons mostly going to be fat. And then we have progressively less fat as fat is removed from starting with VLDLs. And then intermediate, so very low density lipoproteins, and then intermediate density lipoproteins. So over time, we're removing fat, we're removing triglyceride from these, and putting it into the tissues. LDLs and then HDLs, which are going to have the least amount of triglyceride. Anybody remember what is like bad cholesterol versus good cholesterol?
I think HDL is good cholesterol.
Mm-hmm. Yeah, and HDL is good cholesterol because it's mostly protein and phospholipid, has very little cholesterol and very little triglyceride. Whereas LDLs are bad because they have tons of cholesterol. They have the most cholesterol of any of these guys. Yeah. Questions here? Okay. Next. Okay, so here's another schematic. So fat is uptaken, chylomicrons entering the lymphatic system. And then we're going to go into the bloodstream where they will enter the liver. And then triglycerides. So some triglycerides are going to be broken down by lipoprotein lipase. And then we're going to get fatty acids and glycerol, which can be uptaken into the body cells, stored as energy, stored as the triglycerides or used for energy. And then if the chylomicron goes to, or once the chylomicron goes to the liver, here's my cat, then we'll start to make, the liver will make VLDLs. So the liver is really what's changing chylomicron into very low density lipoproteins. And then as we go through the bloodstream, we're going to start removing triglycerides from our lipoproteins. So you can see progressively, like we were saying, less triglycerides. And then so we get the intermediate density, and we're going to remove some more triglycerides, and we get low density lipoproteins. And then eventually, and we'll say uptake some of that, and then we can take cholesterol from the low density lipoproteins and use them in the cell. What do we use cholesterol for in the cell? Two main roles.
Steroid formation.
Steroid formation, so precursor for steroids. And then what do we also use cholesterol for?
Membrane fluidity.
Membrane fluidity, membrane integrity, exactly. Does cholesterol tend to increase fluidity, decrease fluidity, or regulate it in the middle?
Depends on the temp.
Depends on the temperature. So at high temperatures where the membrane becomes too fluid, cholesterol is going to make it less fluid, right? At low temperatures where the membrane is not fluid enough, cholesterol is going to make it more fluid. Then cholesterol really is there to keep things in the middle, keep things at a happy medium, keep it fluid at both low and high temperatures. Excellent. And then HDL is going to be recycled back into the liver, where we can use the proteins and the phospholipids to assemble new VLDLs. Any questions here? All right, so that was digestion. I guess one thing I didn't mention was amino acids. So we know glucose can be transported in the bloodstream, no problem. Amino acids, they call them free amino acids, just like free fatty acids can also be transported in the bloodstream. And those guys have a charge, and they're small because they're just amino acids. So we have no problem with those going through the bloodstream. Okay, time for glycolysis. So that was a little refresher on digestion. So the net reaction of glycolysis. Anybody remember how many ATP are produced?
I think it's 2.
2 net.
It's actually 4, but 2 is used up.
Excellent. Yes. And then what does glucose become at the end of by the end of glycolysis?
Pyruvate.
Pyruvate. Excellent. So here's our net reaction of glycolysis. We have glucose, 2 ADP, 2 NAD+. So we will reduce 2 electron carriers in this step as well. And then 2 phosphates. So the ADP and the phosphate is going to join up to become ATP. NAD+ going to get reduced to NADH. And then glucose is going to become 2 pyruvates. There's 2 main phases of glycolysis. There's the investment phase, which is steps 1 through 3, in which 2 ATP are consumed. There's the payoff phase in steps 4 through 10. And what you want to keep in mind is that as soon as aldolase, which we're going to get to in a few slides, as soon as aldolase has broken the molecule of glucose into 2 3-carbon molecules, every step is happening twice for steps, really step 5 through 10, because step 4 is where we break it into those 2 3-carbon molecules. 4 ATP are produced in the payoff phase. So that's why we have a net of only 2. And 2 NADH are obtained, which will go to the electron transport chain. So what steps do I have to know for glycolysis? What intermediates do I have to know? What enzymes do I have to know? Do I have to know it all? Can I get by with knowing the major steps? Yes, you can. You can certainly memorize the major steps. There are a couple steps that are just not as important or not as highly tested. However, in my experience, personally and with students, it's a lot easier for them to memorize glycolysis as a complete narrative than as discrete steps. So I would recommend that when you are memorizing glycolysis, just go through the whole thing, because it actually, having that whole framework makes everything stick better and longer. And every cell in the body does glycolysis. Do red blood cells do glycolysis?
That's a trick question.
They do glycolysis, yes. Yeah, because we just did say every cell in the body does glycolysis. Do they do the citric acid cycle? Do they have a mitochondria? Nope, no mitochondria. So they also can't do the electron transport chain, but that's not a problem. They're not even doing the citric acid cycle. What did the red blood cell do with the NADH from glycolysis? They don't have an electron, they don't have a mitochondria, they don't have an electron transport chain, right? So they're just going to recycle it. They're just going to recycle the NADH. Do red blood cells, do they have a nucleus?
No.
Also no. Yeah. Okay, so here's going to be our overview of glycolysis. This is the best diagram that I found out there for glycolysis. The only problem with this diagram is that I can't find it in a super high resolution. So like a few of these bonds that are actually double bonds, they just look like thick, like single bonds. But just keep in mind that the thick single bonds are actually double.
I mean, it also doesn't tell you which steps are reversible.
Yes, it's we will. There is going to be like another diagram that I have that does give you like glycolysis down and gluconeogenesis up. We'll be going over that next week. Yeah, I mean, there's no diagrams perfect. This is my favorite, especially because it has some delta G values on here. Yeah. So step one, hexokinase. So the game that we're going to be playing is we're going to look at the enzyme name and we're going to guess what it does based off the name. So what does a hexokinase do?
Breaks up glucose.
So what does the hexo mean?
Six-membered ring.
Six-membered ring, good.
Yeah.
And kinases, what do they do?
Phosphorylate.
They phosphorylate. Did they just pick up a phosphate that they found on the side of the road to phosphorylate, or do they ATP hydrolysis?
ATP.
Yeah, so kinases versus phosphorylases. We want to remember phosphorylases, they just hand you a phosphate they found on the side of the road. Whereas kinases actually are coupling energetically unfavorable steps to ATP hydrolysis. Perfect, so that's what we have in step one. We can see that ATP is being hydrolyzed. Would this delta G still be negative without ATP hydrolysis?
No.
No, right? So they don't give you the units here, but it's actually in kilocalories per mole, kcal per mole. And ATP hydrolysis has a delta G naught of negative 7.5 kcal per mole. So without ATP hydrolysis, we'd actually have a positive 3.5 for the delta G. So ATP hydrolysis is what's making this reaction favorable. And it's not only that we're coupling it with ATP hydrolysis, there are some cases where we'll utilize ATP hydrolysis, but we won't actually put the phosphate onto something. In this case, we're also getting our phosphate that we're adding to glucose from the ATP. Why does ATP have high energy phosphates? Why are the phosphates high energy in ATP?
I think there are 3 phosphates there.
3 phosphates, yeah. So why are they so high energy? What's the charge of a phosphate? Yeah, negative charges repel, excellent, yeah. And then additionally, when you hydrolyze ATP, phosphate has a lot of resonance stabilization of the negative charge. So it's not only that the ATP is so unstable, right? It's also that the product of ATP hydrolysis, phosphate, is also very stable on its own. It has a 3- charge, but it can handle that very well using resonance. Yeah, you can think of ATP as like the liquid currency of the cell, whereas like your bank account, or no, your stocks, whatever the opposite of liquid currency is, your stonks are like triglycerides and glycogen, where you have to actually do some steps to make them liquid, to make liquid currency like ATP. So turning reaction favorable, we said this. Any questions on step 1?
Just keep in mind that because we are coupling it with the ATP hydrolysis, this is an irreversible step.
Yes, correct. So we're going to do a different step when we get to gluconeogenesis, and we want to reverse this step. Thank you for pointing that out. Step 2.
Oh, do we? Oh, I'm sorry.
So,
Do we have to know? I'm not sure if we have to know this, but don't we have to know that like glucokinase is used in the liver?
mhm. Yeah. So when we get to
that's probably something we gotta do too.
exactly, for sure. So when we get to glycogenesis is when we'll start talking about glucokinase. Yeah. By the way, what would inhibit hexokinase? What would allosterically inhibit hexokinase?
Maybe a large amount of, oh, wait.
So in other words, how is this enzyme regulated? ATP, yeah. So ATP is a allosteric inhibitor of hexokinase. Why? Why would ATP inhibit hexokinase?
Because the point of I'm sorry,
No, thank
because
you.
the point of glycolysis is to generate ATP for you. So if you have enough of that ATP, then why make more?
Yeah, it's like if you have $500 in your wallet, you wouldn't want to go to the bank and make a transaction, right? Cool. And then what would be, so another one could be the product, glucose 6-phosphate will also inhibit hexokinase. What would promote hexokinase action?
The presence of ADP or presence of AMP.
ADP, AMP, as well as glucose, excellent. Step 2, phosphoglucose isomerase. So based on the name of this guy, what do we think it does?
I think it transfers, it's isomerase, so it transfers functional groups, I think.
That be isomerase or transfers? So that'd be transferase, right? So what are isomers?
Isomers have the same molecular formula, but have different connectivity.
Excellent. Yeah, different connectivity or different arrangement or like different orientation. Because so isomerases are going to convert between constitutional structural isomers, but we can also have stereoisomers, right, which have same connectivity but different orientation. But here, yes, we're going to be talking about structural constitutional isomers. Yes, so transfer of groups in the same compound. I like that. Yeah. Isomerases could transfer groups in the same compound. Yeah, isomers interconvert, especially tautomers, right? So tautomers are isomers that can readily interconvert. What's the example? What's the main example of tautomers?
Keto-enol tautomers.
Keto-enol, excellent. Cool. So we have a glucose that's been phosphorylated. We're going to isomerize it. What does the glucose become? So glucose 6-phosphate goes to
Glucose 1,6.
ooh, glucose 1-phosphate, that would be in the liver during glycogenesis. So here is going to be fructose 6-phosphate. So substrate is a glucose 6-phosphate, and we're isomerizing it. Isomerases are enzymes that convert their substrate to an isomer. And so therefore, in isomerase catalyzed reactions, there will be no additional reactants or products. And glucose and fructose are isomers. And this is true anytime you have the same number of carbons in a sugar, where one is an aldose and the other is a ketose, those would be structural isomers of each other. So if you have you have an aldoketose versus an aldohexose, wait, hold on, aldoketose, no, that's not a thing. If you have a aldohexose versus a ketohexose, those would always be structural isomers of each other. And then, what was I gonna say? Which one's the aldose and which one's the ketose between these two? Glucose is the,
Oh, glucose is the aldose and fructose is the ketose.
perfect, yeah. And we can kind of see, so if we look at our anomeric carbon, what's the best way to find an anomeric carbon? Looking for a hemiacetal or an acetal. So, and the fastest way to find it, to be a hemiacetal, which we know is a carbon that has a bond to an OH and an OR, is to look first for the oxygen that's part of the ring, and then your anomeric carbon has to be one of the two carbons connected to it. So it has to be either this guy or it has to be this guy. And we can tell it's this guy is the anomeric carbon because it's the one that has two bonds to oxygen, one OR and one OH. And then the anomeric carbon, carbon 1 of glucose, is now here in fructose 6-phosphate. And then carbon 2, 3, 4, 5, 6 from the original glucose. So we have fructose is still going to have the 6' phosphate. Is this reaction exergonic or endergonic? This reaction is endergonic because it has a positive delta G naught. So does that mean it doesn't happen? It's not spontaneous, doesn't happen? How do we know fructose is a keto? Yeah, so either you know fructose is like Fisher projection structure, which has the carbonyl on carbon 2, or you can also tell because the anomeric carbon, OR, OH, the anomeric carbon, there's another carbon coming off of it. So that's another way to tell that it's a ketose. Because in an aldose, there's no extra carbon coming off of the anomeric carbon. My pleasure. So yeah, so how do we explain this? Because we know this reaction happens, like it happens in glycolysis. So how do we explain the positive delta G naught? So let's talk about delta G and versus delta G naught. So what does the naught mean in delta G naught?
Free energy.
So delta G is Gibbs free energy, changing Gibbs free energy. What does the little degree sign mean? This is sometimes it'll be there, sometimes it won't be there, right? Ideal conditions. So yeah, so also known as standard conditions. So under standard conditions is when, or when you have the naught, it tells you that the reaction is under standard conditions. What are the standard conditions? What is the temperature? Is it 0 or 25 Celsius?
25 Celsius.
25 Celsius. What about STP, which is different from standard conditions? Temperature in STP is?
I think that is mentioned in Kelvin.
You measure it in Celsius or Kelvin, but what would it be?
That will be 298 for Kelvin.
So if that be for standard conditions, for STP, the degrees in Celsius is 0, and Kelvin is 273. So STP, does it really like emulate what we normally see in the lab? Are we always working at, because 0 degrees is freezing, right? So are we normally working in a lab and it's freezing condition? I mean, yes, it's very cold often, but no, we're not working at 0 degrees Celsius, correct, yeah. So, so STP, not really useful when we're trying to calculate what would happen if we put something together in a reaction. y'all remember in Gen Chem when you had to go to and you had to do like delta G naught is the delta G of formation of products minus the delta G of formation of reactants. You remember doing those and having to go to the back of your Gen Chem book, looking for the appendix where they have the huge, like multiple page tables. Yeah, brutal to look up so much for those. And then it would always be annoying because it would be like, oh, is it water liquid or is it water gas, water vapor? So those values you were looking up were delta G naughts or delta H naughts or delta S naughts. The benefit of having a standard conditions where it's 25 degrees Celsius, the benefit of having a standard condition be at 25 degrees Celsius, that's going to mirror more closely what's actually happening in the lab or what temperature you're actually doing reactions in the lab, allowing you to get useful information out of these big data tables. There's one more condition for standard conditions, and that's molarity. Does anybody remember what molarity is for standard conditions? So molarity for standard conditions is 1 molar for all reactants and all products. How often do we have 1 molar for all reactants and all products? Is that all the time or some of the time or very rarely? Very rarely, right? And even if you did have 1 molar for all reactants and all products, right? As soon as you started the reaction, assuming KEQ isn't equal to 1, then the 1 molar would no longer be true. So if your reaction is going forward, your reactants would go below 1 molar, your products would go up, and then you wouldn't be able to use standard conditions anymore. So because of this, there's going to be a difference between delta G, which is for non-standard conditions, and delta G naught, which is for standard conditions. And we'll go into how do we decipher this like sort of difference between delta G and delta G naught. And then there's also the prime. So the prime is common with enzymes. And the prime indicates that although like substrate and products are present in 1 molar concentrations, even though they rarely are, certain species would not be present at 1 molar conditions or 1 molar concentrations. What could be some things in an enzymatically catalyzed reaction that would not be present at 1 molar? Some species that would not be present in an enzymatically catalyzed reaction at a 1 molar concentration. What could they be? Liquid and gas. It's a good guess. Maybe if there's like liquid or gas involved in the reaction, like water is not going to be at 1 molar. What else? The enzyme itself, for one thing, right? You're not going to usually have 1 molar of enzyme. You're usually only going to have like, you know, on the order of micromolars to nanomolars, right? Because you don't need a lot of enzyme. Catalysts are reformed in their original state when a reaction's done, right? So you don't need 1 molar enzyme. You wouldn't have cofactors like magnesium be present at 1 molar. You wouldn't have H plus be present at 1 molar because that would be a really, really acidic pH. That would actually be a pH of 0, right? And the enzyme itself, you would not have the enzyme itself be present at 1 molar. Yeah, so that's what this prime that we're going to be seeing in the glycolysis diagram is indicating. So if you see delta G naught prime in the MCAT, don't freak out because there's like another thing in the corner of delta G that you don't know about, because now we know about naught, and now we know about prime. Any questions here? So there's an equation. We know the equation for delta G naught, which is equal to minus RT ln of KEQ. Delta G naught equals negative RT ln K. Delta G also has its reaction. So delta G for non-standard conditions. So if I had 0.5 molar reactant and 2 molar product, I wouldn't be able to use delta G naught. I would have to use delta G. So it does start with or like depend on the delta G naught, but it also depends on reaction quotient Q. So what is reaction quotient Q? It's the difference between K versus Q. So KEQ is the is a thermodynamic ratio of products to reactants at equilibrium. Whereas Q is the ratio of products over reactants at any point in a reaction, whether we haven't reached equilibrium yet, whether we overshot it for some reason, whether we're at equilibrium. We can plug in any numbers to determine what Q is. And then we compare Q to K to figure out, is the reaction actually spontaneous? Because delta G is the ultimate determiner whether a reaction is spontaneous or not. Delta G naught influences it. But by manipulating the amount of reactants or products, we could actually turn a reaction that has a positive delta G naught into a negative delta G. So Q is our reaction quotient. Q equals products over reactants at any point in a reaction. So if we had no products, if we had all of our substrate was reactants at this point, perhaps at the beginning of a reaction, we would have no products, and the numerator would be 0. So that would be a Q equal to 0. So the smallest Q can be is 0. And then the largest Q could be is if we had no reactants. So if we, for some reason, had only products present in our solution, in our mixture, and we had 0 reactants, we'd be trying to divide by 0, which is illegal. Can't do that. I'm gonna call the math police on you. So then that would be sort of the largest Q could ever approach. It could approach infinity if there were no reactants. So we have the spectrum of Q potential values. And then if we go ahead, okay, so let's talk about logarithms. So if we rearrange this equation by plugging in this equation, delta G naught, plug this guy into this slot, and then do some factoring out. We factor out the R and the T. Combining the natural logs, we end up with delta G is equal to RT ln of Q over K. So with logarithms, do we remember if we're plugging in a value that's less than 1, does the log spit out a positive or a negative number when we plug in something less than 1?
Negative.
Negative, good, good. And if we plug in something greater than 1, the logarithm is going to spit out a
Positive.
positive. Perfect. So therefore, if we could say that if Q, the numerator, is smaller than K, the denominator, our ratio would be less than 1. And then the natural log is going to make this negative and spontaneous. So if Q is less than K, delta G is negative, and the reaction will proceed forward via this equation. On the flip side, if Q was greater than K, then we would have a number that's a ratio that's larger than 1, and then this reaction is going to spit out a positive number. So the reaction would not proceed forward, it actually proceed backwards. The reverse reaction would predominate. So in summary, why are we talking about all this? Metabolic steps with a positive delta G naught can be made spontaneous, the negative delta G, by like loading up the reactant side. So you just give it so many reactants, the enzyme has no choice. It becomes favorable. So we can think about this in terms of like law of mass action. You can think about it in terms of Le Chatelier's principle, other things that we're familiar with in terms of how we can make these positive delta G naught reactions spontaneous. So in summary, there's no diagram that exists for this online, which means I probably invented it, maybe. No, I'm sure somebody's done something like this before. Let's go through this. So this is a summary of what we've been talking about. So Q has a range where if it's all reactants and no products, the numerator is 0. And so Q is equal to 0. So the smallest Q could be 0 when they're all reactants, no products. The largest Q could ever be is infinity when there's all products and no reactants. So Q is a spectrum from 0 to infinity, whereas KEQ is a constant for a given reaction at a given temperature. And Q is going to always want to get to K. They want to be equal to each other. They're madly in love with each other or something like sorry, I don't know. Q really wants to become K. It wants to evolve, wants to level up. So when Q is less than K, we're to the left. We have too many reactants, not enough products. So the reaction proceeds forward until it reaches KEQ. If Q is greater than K, we have too many products, not enough reactants. So the reaction will proceed to the left and go back to KEQ. So I love this diagram, this way of like method of thinking about delta G. because this is what determines delta G. I love this diagram because reactants are where they should be. They're on the left side. Products are where they should be. They're on the right side. And then you can just simply know which direction the reaction is going to go to reach that KEQ. Makes sense. Any questions here?
Yeah, I have a question about the reactions from the previous slide. So the first one with the negative RT-LNKQ, I mean, that's one we see all the time.
Yeah.
Like, I'm sure all of us have seen it like 23,000 times. The bottom two, I understand the importance of using those to explain why the positive delta G knots can still continue regardless of there being ATP or not.
Mhm.
Should we know those equations though?
Definitely not the third one. I really can't see them I don't know if I could see them having you like use this third equation on the MCAT. So I would understand it conceptually, not memorize it. I do go through this equation with my students, like mostly just to explain what we're explaining right now. I don't know if you need to absolutely know this one for the MCAT. Can't say I've seen them use it a lot, so I probably just understand these second two conceptually. Yeah,
Okay.
and know they exist. Yeah.
Cool.
Mm-hmm. Yeah. All right. Yeah. So any other questions here? Is this find this diagram helpful? Find it not helpful? Anything I can clarify before we move on here? We're good. Let's jump back into glycolysis. All right. So we explained why the previous step was a positive delta G naught, but it still happens. Next, phosphofructokinase. So what is this guy going to do? What does the bottom that's cut off say? This says delta G equals negative for the, oh, sorry, okay. So when Q is less than K, delta G is negative, so the reaction proceeds forwards. And Q is greater than K, delta G for the forward reaction is positive. We know when we flip a reaction, when we invert a reaction, we just switch the sign of like delta G or delta H or delta S, like Hess's law problem. Sometimes we have to switch the reactants and the products. We change the sign from negative to positive or positive to negative. So if you have a positive delta G for the forward reaction, that means you have a negative delta G for the reverse reaction. Yep, my pleasure. So we have a phosphofructokinase. So this guy is going to add a what to a what?
Another phosphate to the fructose 6-phosphate.
Yeah, from ATP. You can see we have another exergonic step here. We're going from fructose 6-phosphate to fructose 1,6 bisphosphate. So this is our second investment ATP.
It's also reversible.
It's also irreversible. Yep. And what is the other special thing about this step? Once this step has occurred, we are what?
We keep going. We can't go back.
Can't go back now. We're committed. It's the committed step of glycolysis. Yeah. So if PFK is the committed step of glycolysis. And because, for instance, if we'll talk about pentose phosphate pathway, but G6P, glucose 6-phosphate, could also go into the pentose phosphate pathway. Or if we're in the liver, glucose 6-phosphate becomes, for glycogenesis, glucose 6-phosphate becomes glucose 1-phosphate, so it can be stored as glycogen. But once you've done PFK, you're doing glycolysis. You're not doing pentose phosphate, you're not doing glycogenesis. So committed step of glycolysis. And that also makes sense from the perspective of like conservation of energy, not literally conservation of energy, but like for us from a cell's perspective, it wants to utilize energy as most effectively as possible. So as it's invested 2 phosphates and 2 ATPs into a molecule, we don't want to go back now and waste those guys. Question, is fructose 1,6 bisphosphate a reducing sugar?
Yeah, it is because it's a hemiacetal.
Excellent, yeah. So reducing sugars have hemiacetals. You have an OR and an OH. So if we ran a Tollens test on this thing, we can actually open up the ring, go back to the linear Fisher projection version, where we have I guess it's a ketone. It's maybe a bad example here. But aldehydes, when we combine them with silver, they will reduce silver from +1 to 0, and they will oxidize to carboxylic acids. That's actually a really interesting question. And now I have to Google that, because ketone, how would you oxidize that? What'd you oxidize it to? Can ketoses be reducing sugars? Let's learn something together. Let's see.
think so.
Oxidize the carbohydrate, reduces Benedict's solution. Aldose and ketosis. Yeah, it doesn't feel like it should be able to, right?
No, because like sucrose, so to answer this question, I always think of sucrose. So sucrose is like glucose and fructose. It's not a reducing sugar because of that ketose, the ketone on that fructose group.
Yes, well, yeah, and that's because, yeah, because they're both the anomeric carbons are acetals, right?
Yeah. So there's not like a leftover OH to react.
Yeah. Yeah, I'm just a little confused, like, because if you have a ketone, you don't have the extra hydrogen like to take away and make an OH like you would with an aldehyde. Like, how would you oxidize a ketone? Like, normally we say ketones can't be oxidized any further. So that's my personal confusion here. It's because they tautomerize. Okay, they tautomerize to the enol form. No, they tautomerize into an aldose. Okay, cool. Good to go. Monosaccharide ketoses can be reducing sugars as well, because they tautomerize to the aldose version, and then they can be oxidized from aldehyde to carboxylic acid. Make sense? That's interesting. All right, aldolase. So what does this sound like? Any reactions that come to mind? One of our big addition reactions from the MCAT is the aldol reaction. So we have an aldolase. It's probably going to do something about an aldol. And at this point is where we are going to cut our 6-carbon glucose into 2 3-carbon products here. So aldolase. Notice the extremely positive delta G nut. But we know why this is. We know why this works now. Just give it so much fructose 1,6 bisphosphate. Aldolase has no choice but to work on it. We'll make our fructose 1,6 bisphosphate into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, GAP or GA3P, sometimes known, and DHAP, DHAP. Is it a aldol reaction or is it a retroaldol reaction? How can we tell? Retro, right? How can we tell?
You're forming 2 products.
You're forming one product or one reactant into 2 products, because we know with forward aldol, the 2 combine into one molecule. So yeah, so retroaldol, very positive delta G. Any questions here?
I guess my question would be like, what would be the main takeaway from this slide? Just the fact that it's what aldolase does, or I guess what my question is, because do we need to know like how in depth of every step of glycolysis are we expected to know?
Yes, as in like, so would you be expected to like know aldolase converts fructose 1,6 bisphosphate into glyceraldehyde 3-phosphate and dihydroxyacetone phosphate? I would not be surprised if they asked you about aldolase, to be honest.
Okay.
And I think, but maybe the main takeaway would be like that through metabolism, we're breaking down larger molecules into smaller molecules, because eventually we want to get all of our carbons into CO2 by the end. So we want all of our carbons to be a single carbon that's highly oxidized by the end. So in order to do that, we have to start by breaking them down. So this is really the first part where in carbohydrate metabolism, where we're actually breaking things into smaller. I guess we also break polysaccharides into monosaccharides first, but
Cool.
Yeah. And then triose phosphate isomerase. So what is a triose? Three carbon. The OS tells you it's a
sugar.
Sugar. So we got a 3-carbon sugar that has a phosphate and is being isomerized. Okay, so here's our triose phosphate isomerase. And this is between glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. So in the forward reactions during glycolysis, we're going to be converting our DHAP into GAP. Triose 3-carbon sugar. Glyceraldehyde is a 3-carbon aldose. What does the glycer remind you of?
Glycerol.
Maybe glycerol. Yeah. So glycerol is a 3-carbon molecule. Is glycerol also a sugar, a carbohydrate? Is glycerol also a carbohydrate?
Hydrates just have 6 carbon, I think.
Well, yeah, so hexose carbohydrates have 6 carbons, yeah. What's the empirical formula of a carbohydrate? Like CN.
CHO.
So CHO, right? But it's CN, H2N, and then ON. So they have the same number of carbons and oxygens. They have twice the number of hydrogens. So in this case, we have 3 carbons, we have 3 oxygens. Okay, that checks out. N could be 3. But do we have 6 hydrogens? We do not. We have 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So we don't have H2N, because H2N would have to be 6 for that to be a carbohydrate. So glycerol is a polyalcohol, also known as a polyol. And then, so we have a glyceraldehyde. Here's our carbonyl of our aldose. And here's carbon 2 with a hydroxyl group. I thought it's supposed to have, the rest of the carbon is supposed to have a hydroxyl group. Where's the hydroxyl group on the 3rd carbon? Is it there? Is it hiding? The hydroxyl group on the 3rd carbon.
It's part of the phosphate kind of now. It like left because of that.
Exactly, yeah. So it's been phosphorylated. So this is the O of the hydroxyl, but its H has been removed when it became phosphorylated. So very similar to how we know that the amino acids that have hydroxyl groups are the most commonly phosphorylated: serine, threonine, tyrosine, right? They all have a hydroxyl group that gets phosphorylated. And then we have dihydroxyacetone phosphate. So if you remember, our buddy acetone is the simplest ketone. It's a 3-carbon ketone. And this implies, okay, there's 2 hydroxys on acetone. Here's a hydroxy. And then likewise, our other hydroxy has been phosphorylated. All right. So in this step, all of the DHAP is getting converted into GAP. Questions here? All right. All right, now things are going to get a little more exciting. We have a dehydrogenase. What kind of enzyme is a dehydrogenase?
I think it breaks up bonds with water.
So maybe like hydrolysis or hydrolase. Dehydrogenase removing hydrogens. When you remove hydrogens from a molecule, would that be reduction, oxidation?
Oxidation.
Oxidation, right? So we have here is a oxidoreductase. Is it going to oxidize or reduce its substrate? Oh, sorry, we already said that. It's going to oxidize its substrate. Who's getting reduced? Who's getting the electrons?
The enzyme itself.
You go into the enzyme itself.
The NAD plus.
The NAD plus, right? So NAD plus, is that the oxidized or reduced form?
Oxidized.
NAD plus is the oxidized form, good. And then NADH is our reduced form. So we are taking 2 electrons and a hydrogen from our glyceraldehyde 3-phosphate. So it's a hydride. So in this step, okay, we said oxidoreductase. The aldehyde loses a hydride, which is an H and 2 electrons, to NAD plus, which is why we're going from plus to neutral, because the 2 electrons will carry a negative charge on the hydrogen. Where does this H plus come from? Anybody ever get confused as to why it's NADH plus H plus? I know I did. Yep. So when we're adding an inorganic phosphate, we're not adding PO4 3 minus because because we know, okay, so phosphate, we have phosphoric acid, H3PO4. We have dihydrogen phosphate, H2PO4 minus. We have hydrogen phosphate, which is HPO4 2 minus. And then we have phosphate, which is PO4 3 minus. So we have 4 different ionization states of our phosphate. Now the first and the second protons are going to leave at physiological pH. So inorganic phosphate is technically actually HPO4 2 minus. So the other H plus is actually coming from this phosphate when it gets added to the oxidized, so this is actually, was also part of the hydrogen phosphate. So that's where the oxygen also comes from, because notice there's no water, so there's nothing else that could explain why there's another H plus or another O. So the oxygen of the phosphate adds to the carbon, and then the H of the hydrogen phosphate leaves. Does that make sense? All right. So what functional group is carbon existing as right now? What is the name of this functional group?
Is it a phosphoester?
So from phosphate's perspective, phosphate is making a phosphoester. From carbon's perspective, carbon is a carboxylic acid that got phosphorylated. So that's why we call this glycerate. Remember that the suffix ate is indicative of an anion. So it's a glycerate. Glycerate would be a 3-carbon. Glycerate would be a 3-carbon carboxylic acid that has a hydroxyl on carbons 2 and 3. So we have a phosphorylated carboxylate. Yeah. So the aldehyde became a carboxylic acid that got phosphorylated. The aldehyde gained a bond to oxygen. So that is where we're having our oxidation happen. Remember, oxidation, loss of electrons, gain of bonds to more electronegative elements. And then what's really cool about this step is, like, not only did we make an NADH when we oxidize this aldehyde to carboxylic acid, we also get to sneak in another phosphate and make another like super high energy bond here. And now we have 1,3-bisphosphoglycerate, 1,3-BPG. And so now we have 2 high energy phosphate bonds that we can remove from our substrate, which are then going to be doing what to ADP? We're going to phosphorylate ADP later, make some more ATP. And this step, remember, everything's happening twice now. So this step is doing 2 NADHs. Okay, so one of the themes of this lesson, when carbon gains a bond to oxygen, a more electronegative element, NADH is produced. So this is going to come back again and again and again for the rest of Pyruvate dehydrogenase complex, as well as citric acid cycle. Phosphoglycerate kinase. It sounds like it's going to be an enzyme that adds a phospho to a phosphoglycerate. But I thought we already had 2 phosphates. We're adding a 3rd phosphate? I don't think that happens, right? So, like, how do we explain the name of this enzyme?
They like kind of discovered the reverse reaction first, so the name doesn't make sense.
Hell yeah, they discovered the reverse reaction first. And then they decided for some reason to never change the name. And I don't know why that is. Probably just to torture biochem students for decades and centuries to come. Yeah. And this step is where we're getting our first payoff ATP. So if we were naming this for the reverse step, we would be adding a phosphate to a phosphoglycerate. But in this case, we're actually going forward. So we're getting 1 ATP produced instead of hydrolyzed. Questions here? Phosphoglyceromutase. What is a mutase? Kind of another name for what kind of enzyme? Like how do we categorize mutase?
Isomerase,
Type of
yeah.
isomerase, good. Yeah, so mutases are a type of isomerase. So we can expect to see an isomerization happen. And as expected, there are no other reactants or products. So we're definitely doing an isomerization reaction. How do we differentiate a mutase as compared to the overall category, which is isomerase? What's the difference? Mutase is for functional groups. Excellent. So a mutase simply takes a functional group, puts it in a different location in the molecule, which is an isomerization reaction, but that's the specific type of isomerization reaction catalyzed by mutases. Whereas isomerases in general are just converting an isomer to another. So the reason why we call it phosphoglucose isomerase and not phosphoglucose mutase is we actually changed the carbon skeleton from a 6-membered ring of glucose 6-phosphate to a 5-membered ring of fructose 6-phosphate. Questions here?
Just to make sure I understood, it literally takes a functional group from a molecule within a molecule and just moves it to a different location.
Exactly.
Thank you.
Yep. Enolase. So something about enols. What is an enol again? Something about ketoenol tautomers. We can break down enol into ene and ol. So what two other functional groups are present in an enol? Alkene, right, and alcohol. So an enol is a double bonded carbon, an alkene that has an alcohol coming off of one of the carbons of the alkene. So we can expect to see some kind of enol somewhere. So notice what we're doing here is we're actually eliminating water. And so the water we're eliminating is coming from our carbons 2 and 3. So we lose this hydrogen and we lose this hydroxyl group, becoming water. But when the hydrogen gets removed, carbon's actually going to hold on to those electrons and make a double bond with carbon 3. So here's our alkene. Where's our alcohol? It's hiding under the phosphate. So always the best place to look, apparently. What kind of enzyme uses elimination? So we have, what are our enzyme classes? We have transferase, isomerase, oxidoreductase, lyase, ligase, hydrolase, the 6 major enzyme categories.
Lyases?
Lyases, excellent. So lyases are a type of enzyme that breaks bonds using means other than oxidation. And most commonly, it's elimination. Yeah. So the lyase is eliminating the water. If we were going backwards in gluconeogenesis, this is one of the reversible steps of gluconeogenesis. Then we would actually we could describe the enzyme as a hydratase. So a hydratase is an enzyme that hydrates double bonds. And hydratase is a type of lyase. So we could describe it as a lyase in the forward direction or a hydratase in the reverse direction. Hydratases are lyases. I see anything else I wanted to mention? Questions here? So we're making our phosphoenol pyruvate. So pyruvate is a 3-carbon alpha keto acid. 3-carbon alpha keto acid, meaning there's a ketone on the carbon adjacent to the carboxylic acid, which would be carbon 2. They call it phosphoenol pyruvate because it's pyruvate in the enol form that's been phosphorylated. So we have pyruvate kinase. Now, we haven't gotten to pyruvate yet, so we couldn't have, we're not adding another phosphate. So it's reasonable to assume that this is another enzyme that what?
Was named incorrectly.
Yeah, or more specifically, was named correctly, but for the reverse reaction, and
Yeah.
then therefore incorrectly from our perspective, learning glycolysis. Yeah. So pyruvate kinase describes the reverse reaction where ATP is added, or phosphate is added from ATP to pyruvate. Pyruvate, we can see here's the keto version, here's the enol version, and the enol is phosphorylated. Is this step reversible?
No.
Nope, absolutely not. And there's a couple reasons for this, and we'll talk about them when we get to gluconeogenesis. Does anybody remember what the, for the reverse reaction, what the intermediate is? Anybody remember the intermediate for the reverse reaction of pyruvate goes to phosphoenol pyruvate, PEP?
Pepsi K.
So Pepsi K is going to be the second enzyme that converts this intermediate to PEP.
Oh, pyruvate carboxylase, wrong one.
Pyruvate carboxylase is the enzyme that converts pyruvate to this intermediate. What's the name of the
Right.
intermediate? It's an intermediate that's also present in the citric acid cycle.
Oh, citrate.
Close.
Oh,
The thing that becomes-
oxaloacetate.
Yeah,
What am I thinking?
oxaloacetate. Yeah. The thing that becomes citric. Yeah, perfect. Okay, we covered this. We covered this. This is a tautomerization reaction. Pyruvate's an alpha keto acid. Let's see. Okay, cool. So that's back to the overview of glycolysis. Can be overwhelming to be talking about all these steps all at once. But if we think about what's happening here, really, it's not that complicated. We're investing phosphates into our molecule so that as we oxidize it further and change the bonds, we can get more phosphates back. So we're investing phosphate, isomerizing, investing a phosphate, breaking larger molecule to smaller molecules. Then we have, we're getting a reduced electron carrier as we oxidize the substrate. We're paying off some of our ATPs, changing the bonds around a little bit, and then getting another ATP back. So if you think about like the function of all these steps together, I'd say it feels, at least to me, maybe not for everybody, it feels more digestible. Digestible. All right, so let's talk about where all this is occurring. So glycolysis is occurring in the cytoplasm. And we're about to get to pyruvate dehydrogenase complex, PDC. We can see that PDC is on the inner mitochondrial membrane. And then the citric acid cycle, which we'll talk about after PDC, is going to be occurring in the mitochondrial matrix. I am in love with this diagram. Here's gluconeogenesis. Here's electron transport chain. Here's ATP synthase. It's beautiful, beautiful, beautiful. I think I forgot to cite it. Sorry, person who made this graphic. Pyruvate dehydrogenase complex. Oh yeah, so the mnemonic, we'll get to this. I didn't animate it, I forgot. So pyruvate dehydrogenase complex, we have a dehydrogenase. So one of our themes of the day, when we see dehydrogenase, we know it's something that oxidizes the substrate, reduces electron carrier. So we're going to oxidize something in pyruvate, and we're going to reduce, in this case, an NAD plus to NADH. So carbon 1 here, there's a few things going on. Carbon 1 here gets decarboxylated. Here's carbon 3, here's carbon 2, here's carbon 3, here's carbon 2. And then who's getting oxidized? Which carbon's getting oxidized here? Carbon 1, carbon 2, carbon 3. So carbon 1 is going to become CO2. Carbon 2 is actually, originally it had a bond to carbon, but it's gaining a bond to sulfur. So carbon 2 is getting oxidized here. Carbon 2 gets oxidized to a thioester linked to CoA. And here's our theme coming back. When carbon gains a bond to a more electronegative element, such as oxygen, or in this case, sulfur, right? Fonkel-Brish, we know sulfur is more electronegative than carbon. Carbon gains a bond to somebody who's more electronegative than carbon. It gets an NAD plus will get reduced as opposed to an FAD. You do need to know the cofactors. I know, it's really annoying. But there's literally an ANC question that asks you which of the following is not a cofactor of pyruvate dehydrogenase complex. So you do got to know them.
Damn.
Yeah, I know. But here's where our mnemonics going to come in. Somebody taught me this yesterday when I gave this lecture for the first time. The animation is going to be out of order, so I'll just show you all of them. I had to rearrange them so it fit the mnemonic. So we have tender loving care for Nancy. So we have TPP, lipoic acid or lipoate. We have CoA, we have FAD, and NAD plus are the 5 cofactors. So obviously NAD plus's job here is just to receive the electrons from pyruvate and become reduced. Unclear right now what FAD's role in all of this is. CoA's role is obviously to get linked to our acetyl group. So CoA is a molecule that's like, that helps out with transport mainly. When you have a CoA, there's a lot of like transporters that can recognize it. Too late, can't focus now. Oh, that's good too. That's better because like, well, I don't know. Yeah.
Poor Nancy though, she needs her TLC.
Oh my gosh, Nancy. Because yeah, I mean, it's like, it's a little easier to remember too late, can't focus now, because it's like, that's how we all feel when we study metabolism. Tender love and care for Nancy. I mean, yeah, if you remember who Nancy is and that she's getting that good, then you remember that mnemonic too. Cool, so pyruvate dehydrogenase complex, we talked about everything on this slide already. Is only active under aerobic conditions. Why?
Because it's happening in the powerhouse of the cell.
Right, the mitochondria is turned off under anaerobic conditions. Why? Why does it need oxygen? Oxidative phosphorylation, yeah. So what's oxygen's role in metabolism?
It's like the final electron acceptor.
Yes, the final terminal electron acceptor, yes. So if we don't have oxygen, we don't have anywhere that we can send our electrons to. So we don't want to do the ETC, which means why would we want to go into the mitochondria and make acetyl-CoA, which is the main substrate, the first substrate for the citric acid cycle. There would be no point because all of the energy we're getting from the citric acid cycle, with the exception of one measly GTP, has to be from reduced electron carriers, NADH and FADH2. So if we don't have any oxygen in order to receive those electrons, there's no point to running the ETC. So when we talk about the Cori cycle and fermentation, we'll talk about what happens when there isn't anaerobic conditions. But today's going to be all aerobic. And more on the pyruvate dehydrogenase complex. So it's a 3-enzyme complex. There's this lipoic acid that we mentioned before. Not important to know the names of the subunits for the MCAT, just know the PDC overall. And actually, when I did this yesterday, I didn't put it in the PowerPoint, but somebody asked me, why is lipoic acid special? Like, why does lipoic acid get to be in this starring role in the pyruvate dehydrogenase complex? So let's go look at lipoic acid together. And so here's the two form. Oh, this isn't the two forms. Here's the two forms of lipoic acid, the oxidized and the reduced form. So now we can see why lipoic acid is important for this, because we have the two sulfurs. What's another thing that can cross-link SH groups? It's another molecule that can cross-link SH groups and be oxidized. What does this remind us of?
Cysteine.
Cysteine, disulfide bonds, right? So we have a disulfide bond right here. We have two SH groups. So thi means sulfur. All is like alcohol. So thiol is like an alcohol, but with sulfur. So we have two thiol groups. They call it dihydrolipoic acid for the two hydrogens here. It's not because it's hydroxyl. I was confused on that. And yeah, so we can see why this lipoic acid is special. It gets to be here because it can be oxidized and reduced. So overall, we have pyruvate. I know, man. We have pyruvate. Then we're going to give the electrons to this dude, and we're going to give the electrons over here to this dude, lipoate, and then we're going to give the electrons to FAD. And here's where we link the CoA. Give our electrons to FAD, and then FAD is going to give the electrons to NAD. So ultimately, FAD's job is just to be a temporary carrier of those electrons, because ultimately NADH is one getting them. Questions here? Citric acid cycle. So citric acid cycle, we're going to start with a 2-carbon acetyl-CoA, because remember, we decarboxylated one of the carbons from pyruvate. We're going to enter the citric acid cycle combined with oxaloacetate to make a 6-carbon molecule again. 2 carbons throughout the citric acid cycle will be lost as CO2 while the substrate gets oxidized. We will generate 3 NADHs, which will yield 2.5 ATP from the electron transport chain. And we will also generate 1 FADH2, which will yield 1.5 ATP from the electron transport chain. And we also make a 1 GTP. It's not very impressive when you're making like all these guys, which are going to yield multiple ATP, but we do get a GTP, which is an ATP equivalent. And as we'll see when we go over gluconeogenesis, GTP can be used in some parts, some roles in the cell instead of ATP, or not instead of ATP, but sometimes GTP hydrolysis is what we couple reactions with. Mostly we couple reactions with ATP hydrolysis. And the majority of the ATP from carbohydrate metabolism is obtained in the citric acid cycle via these electron carriers. So the citric acid cycle, because it's giving us all these reduced electron carriers, it's going to eventually yield the most ATP, way more than glycolysis. And like the pyruvate dehydrogenase complex, citric acid cycle is only active under aerobic conditions. Because like we said, we're making NADH and FADH2, but I need oxygen. Here's our overview of the citric acid cycle, or the TCA cycle, or the Krebs cycle. If you're old school, I remember when we all called it the Krebs cycle, but we took old white man Krebs's name off of it, and now it's the TCA cycle, the tricarboxylic acid cycle, or the citric acid cycle, depending on who you ask. Here's our tricarboxylics. Step 1 is going to be our citrate synthase. Okay, so citrate synthase, something that synthesizes citrate. What type of reaction is going on here? Here's our 4-carbon oxaloacetate, which is the last intermediate of the citric acid cycle. So the previous round gave us OAA, combined it with acetyl-CoA. Can we figure out where the acetyl-CoA is in this molecule and where was the original carbons from oxaloacetate? So this is all looking very similar to the bottom half of this. We had a ketone combined with an acetyl-CoA. Does this reaction look familiar to anybody who studied their OChem reactions recently?
Is it like aldol condensation?
It sure is. Yep. So we have an aldol condensation happening here. So our alpha carbon of acetyl-CoA will be deprotonated, presumably by somebody in the citrate synthase, one of the amino acids in there in the active site. Going to be deprotonated and then attack the carbonyl, breaking the pi bond, which will then subsequently be protonated, become this alcohol here. We have an aldol condensation. And then the S-CoA is going to be hydrolyzed by water. So we'll replace the S-CoA now, because the S-CoA is really just there when we transport acetyl-CoA into the mitochondria. And then our COO minus here came from hydrolysis of the thioester. Question, is citrate chiral?
No.
No, good. So this is 2 hydrogens. No, this is not even sp3, not even sp3, 2 hydrogens. And then the only guy who looks like a maybe could be stereocenter is this one, but it's symmetrical. We have 2 of these groups, so not a chiral molecule. Questions here?
Yeah, because my orgo is a little rusty. So condensation is when you use water, and dehydration is when water is, I guess for lack of better words, like is a product.
Yes, yeah. So technically, it's only the first half of aldol, the addition part that's happening here. Because the second half, the condensation, we would actually be losing a water somewhere. So yeah, so technically it's only the first part of aldol condensation. Yeah.
Okay.
Great question.
All right, cool.
Aconitase. Can't really tell what this guy's going to do by the name, can we? It's going to aconitize something? No. So here's aconitase. What kind of that? So we have loss of water, but then the water comes back in. What kind of enzyme is this?
Is it also a lyase?
It's also a lyase. So that's why I like that they included cis-aconitate, even though I don't think it's important you know about aconitate for the MCAT. That's why I included it here. Because if you didn't see that intermediate, you would assume that aconitase is what kind of enzyme? You might assume that
An isomerase or something.
it's an isomerase. Yeah. So we first eliminate the water, which is how we can tell it's a lyase, because lyases are enzymes that do that, and then do a couple other things. And then, but we add the water back, so then we hydrate the double bond. The purpose of that is to shift our hydroxyl to an alpha carbon down below here. Yeah, hydratase lyase.
Funny story. I got a question on this on my MCAT.
No way. What do you
Yeah, it was
remember?
the first time I took it, I got a question about like the intermediate of like this step. I was like, oh no, I didn't know that was a thing. So
Oh wow.
it's a
Okay.
good thing you bring it up because it does get asked. I assume it was probably one of those experimental questions that they like to ask and then throw out, but it's possible.
Yeah. Okay. That's good to know. Good. We should know about this intermediate then. I'm gonna just get rid of this.
Yeah, they want you to know, like, I would say these 3 processes pretty well.
Yeah. So yeah, citric acid cycle is huge on the MCAT. Yeah. All right. Isocitrate. Oh yeah, is isocitrate. Oh, you can see the answer. Is isocitrate chiral? It's got 2. Where are the 2 stereocenters? You still have to do that. You can use like directional, like bottom left, top right.
It would be the bottom 2 carbons.
So the bottom left one for sure, and then the middle left one, right?
Yeah.
This dude and this dude. Yeah.
Charlie, quick question about lyase. So I mean, the way we learn it's like it breaks bonds without the use of oxygen and stuff.
Water.
So
or without hydrolysis. Yeah.
Ooh, okay. Can you just expand on that real quick? I'm sorry for wasting people's time right now, but
no, this is the kind of question that we need. So yeah, so lyases are so hydrolases are enzymes that break water in order to break other bonds, whereas lyases will break we'll break certain bonds. In this case, we are breaking the water into an H and an OH, but we're not actually breaking the molecule down. So that's what kind of you could differentiate between hydrolase and lyase.
Oh, okay.
Yeah. So if you see elimination, if you see water leaving, your best guess is a lyase. Or if you see hydration, if you see water entering and hydrating a double bond, your best guess is also a lyase.
Okay. Oh, so when you say hydrating double bond, like it's breaking a double bond?
Yes, breaking a double bond. And then we get an OH here, we got another H here. So that's alkene hydration. Yeah,
right, cool.
one of those it's like one of the very first reactions we learned, I believe, in OChem 1 was like hydration of alkenes, where like you like protonate the alkene first, and then the carbocations, the more substituted, the mark position, and then you add OH to the other side, like Markovnikov hydration of alkenes, but not heavily tested on the MCAT. Like I don't really use the word Markovnikov when it comes to MCAT, because they just don't have a lot of reactions that are mark or anti-mark. Isocitrate dehydrogenase. What is this guy going to do?
Oxidize.
It's going to oxidize substrate, reduce an electron carrier. So where's the oxidation happening on isocitrate? Top left, bottom right. Y'all right? Okay. So CO2 gets lost here. And then we had an alcohol becoming a ketone. So notice, again, theme of the day, you find the bond that got oxidized. We did that. The C5 hydroxyl group got oxidized to a ketone. Carbon who got deeper, sorry to give that one away. It's the one in the middle here. It's the C3's carboxylic acid that's coming off of it. And then we now have 5 carbons after this step in our substrate. So again, our theme, when carbon gains a bond to a more electronegative element, such as oxygen or sulfur, NAD+ gets reduced to NADH. Questions here? So we're now down to 5 carbons. We're going to eliminate, or we're going to decarboxylate another carbon because we put 2 into the citric acid cycle. We need to get around the citric acid cycle and end up with 4 again. So we'll see that in the next step.
Quick question about other slide. Which carbon is getting oxidized?
This guy right here. So there's this was a CH and this was an OH, and we lost these two. These two were dehydrogenated, and one of them went here and the other one went here. And then now, because these guys lost a bond to hydrogen, they gain a bond between each other. How would you name the carbons again? Difficult to know exactly. Like the IUPAC, we would start with this carbon down here, 1, 2, so we could get the hydroxyl on the lowest number, 3, 4, 5 for the longest chain. That's the IUPAC way. I don't know if they would. I don't know if you would number it like in the like top to bottom way or the IUPAC way. Yeah, I've been doing it top to bottom. So. Yeah, I hope that wasn't confusing. Okay, alpha ketoglutarate dehydrogenase is another complex of enzymes. What does this reaction step seem similar to that we've seen already? Pyruvate dehydrogenase complex. So we did, in that step we had an alpha keto acid, which is pyruvate. Pyruvate stops here. It'd be 1, 2, 3. Pyruvate would stop here. So we just kind of have an extra couple of carbons. And then we are also introducing a CoA, decarboxylating a carbon and reducing an NAD+ to NADH. So extremely similar to pyruvate dehydrogenase complex. Um, Glutarate. Glutarate is a 5-carbon dicarboxylic acid. Here's what it looks like. So 1, 2, 3, 4, 5 would be our glutarate. Alpha keto. So on the alpha carbon, there's a ketone. And then we already did this. Oh wait, no. Where's the bond that got oxidized? Carbon 2, what?
To sulfur.
The sulfur, good. Yep, so very similar to our acetyl-CoA step, the carbon that carbon decarboxylates we have carbon getting decarboxylated and replacing it with an S-CoA. Ketone from alpha glutarate became a thioester. And by the way, it's not only is it similar in what it's doing to its substrate as pyruvate dehydrogenase, it actually has the same cofactors. I don't think you would be expected to know alpha ketogglutarate's cofactors, but you know the tender loving care for Nancy, you're too late, can't focus now, mnemonics, then you'd know the cofactors apparently to alpha ketoglutarate dehydrogenase complex 2. So like this is another thing which like, why are you including this, Charlie? Like, why are you including the similarity to PDC or the cofactors? And this is all about recognizing patterns so we can learn this stuff better and it can stick longer. Theme, carbon sulfur bond got oxidized, NAD plus got reduced. Questions here? Succinyl-CoA synthetase. It sounds like it should be an enzyme that's synthesizing succinyl-CoA, but we just made succinyl-CoA in this step. So we're already thinking, oh, another one that got named for the reverse reaction. Thanks biochemists. Right? So synthetases are ligases. Synthetases are ligases. So we're talking about ligases now. What do ligases do?
They kind of combine two molecules.
They combine two molecules. Do they require ATP or GTP? Not or. Do they require a nucleotide triphosphate? Looks like it, right? We know DNA ligase requires ATP, and so synthetases are the same thing as ligases, which use nucleotide triphosphates to join two molecules. So in this case, GTP hydrolysis for the reverse reaction provides the energy for appending CoA to succinate. Another example of enzyme named for the reverse process, but in the forward reaction, we generate one GTP, which is a ATP equivalent. Questions here?
That's so confusing, but it makes sense. So I'm with you.
Hell yeah. Confused, but making sense all at the same time. Where does this oxygen come from? Because we don't have water coming in. So this is the same carbon of this thioester right here. Where does that oxygen come from? Can't be water.
Is it from a phosphate?
It's from a phosphate group. So I had this question for myself when I was making this PowerPoint presentation. So I had, your boy, I had to look it up. So here's what happens in the mechanism. This is just for fun. So if you can follow it, it's fine. Don't memorize anything here. So here we have our enzyme is this little bean, cute bean, small bean. And this looks like the enzyme's not even doing it. Like phosphate is just, like thioesters are a high energy bond. So it looks like phosphate is sufficient to just hydrolyze this bond on its own, which probably implies that that happens almost immediately after succinyl-CoA gets made. So CoA gets hydrolyzed by phosphate. And then now we have our histidine acting as a nucleophile and attacking phosphate, breaking up the bond to oxygen. So here's where our oxygen of succinate came from. It was actually, you were right, from the phosphate. What are the amino acids that can be phosphorylated again?
Serine, threonine. Can tyrosine get phosphorylated?
Yep. Anybody else? I mean, looks like we have a phosphohistidine here. So serine 3 and tyrosine, most common amino acids to be phosphorylated, but here's an example of histidine. So we know hydroxyl groups are great nucleophiles. So that's why serine, tyrosine, and threonine can be phosphorylated. Their OH of their side chain can act as a nucleophile and gain a phosphate. But if you understand nucleophiles and electrophiles, why should it be limited to just hydroxyl groups? Why couldn't the oxygen of a carboxylic acid be phosphorylated? Or why couldn't the nitrogen of a basic amino acid like lysine, arginine, and histidine be phosphorylated? Sulfurs are nucleophilic too, so why couldn't cysteine be phosphorylated? The answer is all of these things can be phosphorylated, actually. Someone lied to you and told you it was just these three. For the MCAT, just assume it's these three unless there's some other context that suggests otherwise. But if you understand nucleophiles, this should make sense as to why other amino acids can actually be phosphorylated. Any questions here? All right, succinate dehydrogenase. This is going to be an enzyme that we already know is going to oxidize its substrate and reduce an electron carrier. Find the bond that got oxidized. Oh, also, well, let's find the bond first.
Is it the carbon to carbon and it became double bond?
Yes. So now we have a variation on a theme. Instead of carbon getting oxidized by gaining a bond to somebody who's more electronegative, like oxygen or sulfur, we have carbon being oxidized by losing a proton, losing a hydrogen, and gaining a bond to another carbon. So we're gaining a bond, we're losing a bond to hydrogen on each carbon, gaining a bond between the two carbons, but now we get FADH2. So this is a variation on the theme. And so it turns out that because carbon and carbon are equally electronegative because they're the same element, we don't get as good of an electron carrier. So there's a lower oxidation potential of carbon to carbon versus carbon to oxygen. So we have to reduce FAD, which is going to yield less ATP than if we had oxidized a carbon to oxygen or carbon to sulfur bond. The greater oxidation potential can produce a better electron carrier, NADH. That makes sense to people?
Usually when we see carbon to carbon, we will think of FAD.
Exactly.
Okay.
Yeah. Where is succinate dehydrogenase located? Is it in the mitochondrial matrix?
It's in the inner membrane space, the second. I forgot what they're called. They're like four components.
Complex.
Yeah, that thing.
Complex 2.
Complex 2.
Exactly. So yeah, so succinate dehydrogenase is literally complex 2 of the electron transport chain. So it's on the inner mitochondrial membrane. Oh, yeah, I forgot to put the answer. It's on the next slide. Cool. So new theme, carbon-carbon bond got oxidized, FAD got reduced. We're going to see this again when we come back to beta oxidation in 1 to 2 weeks from now. Carbon-carbon has less oxidation potential than carbon-oxygen because oxygen is more electronegative, so it's a greater oxidation than carbon-carbon. So therefore, we're getting an electron carrier with a lower oxidation potential. So that electron carrier is not going to be able to enter at complex 1 like NADH can. FAD is going to enter or is going to send its electrons into the electron transport chain at complex 2, which is where this is all happening. So this is going to be our sort of new theme that'll apply to beta oxidation as well. So therefore, we're yielding less ATP because what is complex 1 doing other than receiving electrons from NADH?
Pumping
What is it?
protons.
Pumping protons, right? So we get less ATP from FADH2 because it doesn't get to get the 4 protons from complex 1 because its oxidation potential is not as great. So it doesn't want to lose electrons as badly or as early in the electron transport chain as NADH does. And all of this is coming from these differences in electronegativity between the bonds getting oxidized. Yeah, go ahead.
So complex 2 is what creates the FADH that in turn reduces itself.
Yeah, let's elaborate exactly. So succinic dehydrogenase, we'll refer SDH, is complex 2 in the electron transport chain. It's the only enzyme that participates in both the citric acid cycle and the electron transport chain. So we have our succinate goes to fumarate, the carbon-carbon bond getting oxidized. Electrons are going to first go to FAD, which is actually just really a temporary, like we always see FADH2, FAD on that like reaction arrow of citric acid cycle. We're never always really thinking about like how long does FADH2 get to hold on to those electrons? Bro, it's immediately giving those electrons to the iron sulfur clusters in the complex 2. So it's really just a very temporary electron carrier.
Gotcha.
And ultimately, yeah. And ultimately, we're going to give those electrons to, who is this?
What was your question?
Who's this guy right here?
Coenzyme Q.
Coenzyme Q, also known as
Ubiquinone.
ubiquinone. Perfect. So, so SDH couples the oxidation of succinate to fumarate with reduction of coenzyme Q. Coenzyme Q is also known as ubiquinone, gets reduced to ubiquinol. FAD is sort of the intermediary in this process. It's not getting those electrons for very long. So here are ubiquinone and ubiquinol. I heard it through the grapevine that this was tested on an MCAT last year. So you do need to know this structure as well. So we have the ketones and we have the alcohols. So ubiquinone has the ketones, ubiquinol has the alcohols. From what I heard, it wasn't that they were testing ubiquinone versus ubiquinol, which is actually pretty easy if you like own and all from like nomenclature, right? It was more so like picking out from a crowd of molecules which one corresponds to ubiquinone.
So quick question, is it recognizing the, for example, like in OWN, it's 2 double bond O's with the 2 double bonds, and then in all, it's the aromatic ring with the OHs. Is it a matter of just picking that out, or do we have to be able to recognize, the unsaturated chain with like the methyls throughout it and stuff like that?
Oh, that would be hard. No, it's more like, do you know that, can you tell that it's like coenzyme Q as opposed to like coenzyme A? Or as opposed to like FAD or like NAD. It's more like that.
Okay.
Yeah.
So when you say coenzyme Q, so you're just like recognizing that coenzyme Q is the first one.
The first one to receive electrons from FADH2, yeah. Because there's still going to be complex 1 over here, right? Sorry, no, I understand. The first one in this figure.
No, I'm saying like in regards to the structure. You said we need to know the structure.
Yeah, but it's more like picking it out of a crowd of different macromolecules or different like coenzymes, like NAD, right? Is nicotinamide adenine dinucleotide. So you would be able to tell immediately this isn't NAD because it doesn't have an adenine or ribose or two nucleotides. FAD, flavin adenine dinucleotide. You'd be able to tell it's not FAD, right? Coenzyme A. Actually, forget what coenzyme A structure is. Wow, how did they know? Coenzyme A is a single nucleotide with a few amino acids linked over here. So it'd be more like, can you tell that like ABCD, and they give you NAD structure, they give you FAD structure, they give you ubiquinone structure, and they give you coenzyme A structure. Like which of the following is ubiquinone? That's what you'd be expected. You wouldn't have to be like, how many double bonds are in the hydrocarbon tail of ubiquinone? Yeah, nothing like that.
So we should also know NAD and FAD then.
Yep, 100%. Definitely got to know those.
Awesome.
And when you do electron transport chain, we'll look at oxidation and reduction of NADH reactions, FAD reactions, as well as obviously the structures when we talk about those reactions.
Oh, okay, cool.
Yeah, I think the reason why they want you to know that what coenzyme Q looks like is because like of the quinone, and they expect you to know the structure of a quinone. Also, I remember on my latest exam, they do ask you what flavin looks like.
Yep,
That's another one too.
exactly.
And flavin's the FAD, right?
Yeah. So flavin is part of the flavin adenine dinucleotide.
Cool.
I mean, we can just glance at these structures really quickly. Like, I knew we were gonna take our time here today, and I appreciate everybody's attention and all these great questions. All right, so flavin adenine dinucleotide.
Dude.
So we have, okay, this is not the best way to look at. Oh yeah, they do in the FAD structure. This is the other ribose. So that's why it's a dinucleotide, but they show it in the Fisher projection for reasons, I guess. And then so this is the flavin part, I believe.
Yeah, that's the flavin part.
The tricyclic ring system. Yeah. And then here's nicotinamide adenine dinucleotide, much more obvious that this guy's a dinucleotide. Here's our adenine, and then here's our dinucleotide. And so this is our nicotinamide. Oh, wait, it's right. Yeah, nicotinamide. Yeah.
And this is the one that's before it's reduced, right? The NAD plus?
Correct, yeah. We could look at the reduction reaction here. So this is the part that's gaining the electron, the hydride. This is the H of NADH is one of these guys.
Okay.
Cool. Okay, yeah, I'm glad we took that little detour because it's nice to have a face for the name, isn't it? All right, fumarase, almost done. So fumarate, we got our alkene in the middle here. What kind of enzyme is fumarase?
I want to say lyase so bad.
Why?
Just because.
So we have input
Well,
of
there's
water.
going in.
Yeah, there's water going in. We're losing a double bond. So that's the opposite of a water elimination. This is a hydration. Fumarase hydrates the alkene formed from the previous citric acid cycle step, probably hydrating this because we want to oxidize this bad boy in a second, right? So it's a hydratase. Because remember, hydratase and lyase, hydratase is a lyase. And so a hydratase is something that hydrates. We'll see hydratase come back up in beta oxidation as well. So alcohol elimination and hydration are done by lyases. We saw aconitase, we saw enolase. Questions here? All right, and then malate. Oh, sorry, and the one that's hydrated is the malate. Malate dehydrogenase is going to be an enzyme that oxidizes a substrate, reduces electron carrier. So here we have it. And then very similar to some of our other dehydrogenase reactions from carbon to oxygen oxidations. So we can see here the two hydrogens gaining a bond between carbon and oxygen, and here are the two hydrogens after we've taken them and 2 electrons to reduce NAD+. So here's the theme again, and this is the final step of the citric acid cycle. What we're going to see when we cover gluconeogenesis is oxaloacetate can also be used in gluconeogenesis. And it was that sort of is the intermediate in gluconeogenesis of the irreversible pyruvate kinase step, where we go from pyruvate to oxaloacetate and then back to PEP. Questions here? So overview of our citric acid cycle now. Got a 2 carbon and a 4 carbon, making a 6 carbon citrate. The aconitase reaction is a net isomerization, but we know now it's a lyase that actually does the work. And then we are starting to remove 1 carbon, getting an NADH by oxidizing this bond, remove a 2nd carbon as CO2 decarboxylated, reduce another NAD plus to NADH, and here was the thioester that became oxidized. And then we are using the energy of the thioester to phosphorylate GDP into GTP. And then we're going to oxidize an alkene, or a carbon-carbon to an alkene, getting an FADH2, hydrate it, oxidize the last guy over here, and then we're back to the start. So we're painting a picture. We have a narrative we are going from larger molecules to smaller molecules. Carbon is eventually becoming CO2 in all these molecules. As we oxidize carbons, we are reducing electron carriers, which we will then use in the electron transport chain. Okay. So that's
Charlie, when you say use the word narrative, do you mean understand what's going on? Is that what you mean?
yeah, tell it like it's a story. Yeah. So we've been going through the story of A, B, C, D, E, F, G, H, I, J, K, L, Z, as opposed to being like, you know, I memorize reaction A, reaction B, reaction C. So the narrative is like following it through the entire process, and really understanding what's happening in every step. Yeah, you may not get tested on every step of glycolysis, but in my opinion, having worked with a lot of students, it's a lot easier if you're focusing on like, why is everything happening?
Yeah.
Yeah, it's painstaking work. We had to talk a lot about some oxidation concepts that were probably foreign before we did this. It's painstaking work, but with this level of understanding, at a certain point, you just know it. Yeah, you might have to practice it a couple more times. But yeah, I find it easier this way, the narrative way. Okay. So we'll be starting with gluconeogenesis next time. And then fermentation. I would say let's just have the session at the same time next week, and then probably the following week as well. So if you were here for this week, we'll be showing up at the same time next week and the following week, and continuing our metabolism series. And so we're going to try to get through at least pentose phosphate pathway. We're not going to get through these. I was really ambitious. I was like, hey, everybody, let's do all of metabolism in 2 hours. Originally, and then it got narrowed down to, I thought I was going to get through gluconeogenesis. That didn't happen. It got narrowed down to just these three metabolic processes. But yeah, hopefully you had fun with this. Yeah, I'll try to have this on YouTube by the end of the evening.
Cool.
So probably for those of you who are at Eastern time, you're not going to see it till tomorrow. But yeah. Yes, I have only uploaded one video to my YouTube currently. That's the oxidation video. So I sent that out to a couple different group chats because if you want extra background on all this redox stuff, reduction oxidation, more electronegative, less electronegative, yeah, that is a great review of reduction oxidation. Like I thought I understood reduction oxidation until like I took a Berkeley review MCAT course. And then B, like I started teaching it, and then I realized I didn't understand it as well as I thought I did. So all of my best nuggets and examples and my understanding of oxidation is in and reduction is in that video. So yeah. Any questions before we close things for tonight?
Yeah, one quick one.
Mhm.
So we said RBCs, they don't do, CAC because there's no mitochondria. They do fermentation though, right?
Yeah, they do. I believe they would have to do fermentation because how would they recycle their, we'll talk about fermentation next time. How would they recycle their NADH that gets made by glycolysis? Because they don't need that NADH. They're not going to do anything with it, right?
Oh, true, because NADH is what's used to turn pyruvate into lactic acid, right?
Exactly. So they probably are going to do fermentations. I was actually wondering that when we were talking about it earlier, but
Yeah.
well, I mean, like, why don't we fermentation in red blood cells?
Yeah, thinking about it in the way of like recycling NADH and stuff like that, kind of, it makes sense. It like kind of fits the narrative now, like how you put it.
Yeah. Oh, sorry, I'm not sharing my screen anymore. Yeah, red blood cells, they say always, so that's a great question, always use lactic acid fermentation to regenerate NAD+ because they lack the mitochondria needed to undergo aerobic cellular respiration. So in other words, red blood cells are always in fermentation in anaerobic mode.
Gotcha.
Yeah.
Cool.
Any other questions for tonight? Yeah, people in the chat, my pleasure. I mean, I love this stuff. I love metabolism. Once I got over my fear of it and actually like take a deep dive, it became a lot more interesting and fun. Love to share that excitement, enthusiasm with people.
Sweet. Thanks again, Charlie. You're the man.